All right, so for section 3.5, everything that we've done so far has been one variable. So I was mentioning the ages of students in a class or something like that. Well, what happens if we've got two variables in play? So I'm just going to use the example from the book. The example from the book talks about a man who owns a store, and he has multiple commercials running over the weekend, and he wants to see if there's an effect by, lesser commercials result in lesser sales, or more commercials result in higher sales. So he's wanting to see if these two variables are working together. So what we have is essentially a lot of the same thing. We're just adding a second variable into it. So we've already done variance. Well, now we're going to call it covariance because we're working with multiple variables. And we've got sample and we've got population. Okay, so what you saw before for variance was that portion, and we also squared. What am I trying to say? We squared that value up there. Okay, so you're still going to determine what your mean is for one variable. You're going to determine your mean for the other variable. You're going to take each data point and subtract off the mean. Take each data point and subtract off the mean. Multiply those two numbers together. Okay, so you may end up with 10 of those numbers. Now add all 10 of those together. So if you will notice, this book is a very valuable resource, okay? Because what they're going to do is they're going to show you really, really great ways for you to organize this stuff. So in this case, you have values for x, you've got values for y. And then you're going to take your x value and subtract off your mean. Take your y value, subtract off your mean. And then take these two numbers and multiply them together. Okay, so that's where we're at right now. All you've got to do is add that column up and get your answer, which is kind of hard to see, but your answer is 99. So this whole thing right here, this mess turned into a 99, and then you divide it by one less than the number in your sample. Well, we had 10 units or 10 data points in our sample, so we divide it by 9, and we get 11. So that's our sample covariance. Your population covariance is going to be in Greek because it's population. Okay, so what we have is the sum of the product of each of these things. So we have your x data point minus mu for x. Okay, your y data point minus mu for y. You're going to multiply all those, add them all up, and then divide by the actual number in your population. Don't subtract 1. Okay, so that's going to give you a number for your covariance. But again, that's going to be dependent on what you're measuring, that type of thing. So it's going to be this weird number that it kind of feels like it really doesn't have much to say. Well, your covariance is actually going to reflect. And if you'll notice, we were plotting these 10 points that I just showed you down here, and you've got this nice little track. If you notice, it makes almost a straight line. All lines are straight. It makes a diagonal line moving in an upwards motion. So that kind of sort of tells you immediately if the number of commercials increases, your sales are going to increase. Okay, so you're looking at that as a positive correlation. Now, let's talk about that for a second before we move on to the correlation coefficient. You can look at this and kind of sort of look and see what's happening here. This is a very positive movement. The closer this is to a line, the more reliable your data, the more reliable your conjecture is. Now, let me put a little caveat on there. There's a saying in statistics that correlation does not equal causation. Okay, correlation does not equal causation. So these two things may have absolutely nothing to do with each other. For instance, the temperature in Texas in the summer, okay, is going to increase. And then the weight of children as they grow up increases. Well, those two things have absolutely nothing in common. But you're going to notice as the temperature goes up, the weight goes up. There's no cause effect there. Okay, so the saying in statistics is that correlation does not imply causation. Okay, just because the temperature is increasing doesn't mean these kids are gaining weight. They're gaining weight because they're growing. Okay, now take that out of there and let's just say that if the variables are related, if this is moving in an upwards positive direction as you read it from left to right, then you've got a positive correlation. The closer that makes to a perfect line, the more closely related that relationship is. Okay, this data is all over the place. Okay, there is nothing. There is nothing. So this would be approaching, this is positive. Okay, we're going to say this is like buckshot. Okay, this is no correlation whatsoever. It's all over the map. Okay, now we look at this one. There's a negative correlation. As you read this from left to right, your data points are going in a downward motion. So that's a negative correlation. Now, what are we going to do with that? We're going to look at the correlation coefficient. And what that does is it's not affected by your unit measure. So a while ago we were looking at, okay, sales, and we were looking at number of commercials that were broadcast, or we were looking at temperature versus weight, which is not correlated. But what the correlation coefficient does is it's going to give you a range from -1 to +1. Okay, so a -1 is a perfect negative correlation. Okay, perfect negative correlation. Okay, a correlation of 0 means it's like buckshot, it's everywhere. A correlation of +1 means it's a perfect line. So let's look at that for a second. When I show you this picture, these are just 3 data points, but they make a perfect line. So this thing has a perfect positive linear relationship, and its correlation coefficient is 1. Okay, so if I look at this one back here, I would say that's pretty much a good line. Okay, I would say that's probably in the 70s. Okay, I would bet without doing any math that your positive correlation coefficient would be something like 0.7. Okay, this is going to be 0. Okay, this is going to be -0.7. It's pretty much there. Okay, you can see the line, but it's not tight and close, and it doesn't make a perfect line. So how do we figure this thing out? What we do is we use, for a sample, we're going to use R, okay, and we have a subscript of XY because we've got 2 variables. So what you're going to do is you're going to do the sample covariance on top, and then you're going to divide it by the product of the standard deviation for your X samples, and then your sample standard deviation for your Y. Okay, so this is going to be your sample covariance divided by the product of your sample standard deviation for X and your sample standard deviation for Y. Okay, so let's move to population. Okay, so these are 3 things that you now know already how to compute based on what we've done in previous sections. So let's look at let's look at population. This is not a P. Okay, this is actually a Greek letter called rho, and it's spelled R-O-H. So notice that this is an R, and this starts with an R when you say it, but it's rho. Okay, so it looks like a P, but it's rho. So because we're talking about population, we're dealing with Greek. So I look at rho sub xy, and I find out that I've got my population covariance, which we just figured out how to do a while ago. So here's your population covariance. There was your sample covariance. Okay, divided by the product of your population standard deviation for X and your population standard deviation for Y. When you do these, you will generate answers that will go anywhere from -1 to +1. Okay, the closer to -1 it's a perfect negative correlation. The closer to +1 it's a perfect positive correlation. And if you hit 0, that means there is nothing going on. There is no relationship. Okay, because it's buckshot. It's everywhere. There's no correlation whatsoever. So 0 means nothing. All right, so that is 3.5. And once again, let me know if you've got questions. Please use Excel if you don't have the embedded software. A lot of the problems as we go along will have embedded software for you to use. It'll just be a blue link. And I mentioned that before. But if you don't have that, then use Excel to do this stuff. Otherwise, you're going to be, you know, writing on several reams of paper for days. But use Excel to your advantage. So I will see you in chapter 4.